All right, welcome back, everybody. Our next speaker is Maryam Kamgarpour. She's a professor at EPFL, leading the Sycamore Lab. Her research interests include multi-agent learning, reinforcement learning, and control. Looking forward to your talk, Maryam.
Thank you very much. Good morning, everyone. Thank you for the invitation, and it's a pleasure to share my work with you. Um, so, my motivation for research is that as we increasingly automate our society, we have increasing amount of uncertainties that we have to manage and control. For example, in a smart grid, this uncertainty could be from the output of weather-based renewables, solar or wind, or it could be from in a smart intelligent transportation network, it could be from trajectory of the nearby traffic. Um, these uncertainties could also be from interaction of number of different decision makers, such as in intelligent transportation system or in multi-robots. So my work is on developing algorithms that guarantee safety and also coordinate interactions. And the focus of this talk is coordinating interactions through multi-agent games. So let's just get started. A multi-agent game we have n players, let's say 1 to n. Player I has her action AI in the set capital AI, and the joint action is always denoted by boldface A. So AI is action of player I, A minus I is the action of everybody else. And she has a cost function, J superscript I. Okay, such problems arise, for example, in auctions. Here, the action of each player is the bid that they place, and the cost or reward is whether they get the item and for how much. Similarly, in a traffic scenario, the action and the cost of each player depends on the action of the other player. So it's a multi-agent setting.
So do you assume everybody knows all cost functions?
I'm gonna exactly right here. Perfect. So, what's the problem of learning in games? So, we're gonna consider the case where player I does not know JI, not even her own cost function, but can query it. Okay, so she can. It's like a black box setting. Player I can play AI and receive JI evaluated at AI and A negative I. So this situation arises because sometimes the cost functions depend in non-trivial way on the action of others. For example, travel times in a transportation network depend on road congestion, and this may not be a priori known. Similarly, electricity price in a smart grid is not known. The functional form of this price is not known in advance, but players can make certain consumption or production and then measure their costs afterwards. So the question here this talk addresses is how do players learn to optimize their decision? And I'm going to talk about learning in convex games and then learning in non-convex games and conclusions. So let's start with convex games. So what's a convex game? So we have the cost function ji is a convex function of player i's decision variable, and we assume it's continuously differentiable in all variables. And the capital AI, the set of actions, is convex and compact. Some examples of convex game, a mixed strategy extension of finite action game is always convex because the action set of each player is the simplex, and the cost function of each player in her own decision variable is simply a linear function. Okay. But there is also more complicated examples. For example, travel times could be approximately modeled by a convex function in a transportation network, or a price of electricity could be often approximately modeled as a convex function. So this is a convex game. So here we look at a Nash equilibrium, A star, which is a joint action set which no player has incentive to unilaterally deviate from her action. So given actions of other players, A star minus I, player I is optimizing her decision. Okay. So in a two-player zero-sum setting, you can think of this as the point on the saddle. So no player has incentive to deviate. In convex games, we know that Nash equilibrium are guaranteed to exist. Also, and in general, this even existence of Nash equilibria are difficult, but results are difficult. But in this case, at least we know that they exist. And furthermore, we know that they are characterized by the so-called pseudo gradient of the game. So if you stack the gradient vector of each player's cost function with respect to her own decision variable. You get a map from, so D is the dimension of action set of each player, and N is the number of players. So you get the following map M of A, and it's called a pseudo gradient. And we know that a star is a Nash equilibrium if and only if the following inner product is greater than or equal to 0 for every joint action of players. Okay, so if you think of this condition, it looks very much like a first order optimality condition in an optimization problem. But the difference here is that this pseudo gradient in general is not gradient of a single cost function. Okay, and this is one of the main differences between games and optimization problems. If indeed this was a gradient of a single cost function, the game would be potential and it would be easier to address. But we consider the more general case. Okay, so we know Nash equilibria exist and they have been characterized. So now we come back to the problem of learning in convex games, and we want to address how do players learn Nash equilibria. As I mentioned, this looks very similar like the setting of black box optimization, right? Player just plays a policy and then she receives a cost function. So she could possibly think of finite differencing to estimate the gradients using this zeroth order information, right? So she could query her cost at AI and AI plus some W and to estimate the gradient. But in general, in games, actually, you can, in this setting, you cannot do that. Why? Because the feedback she will get at AI um, is ji of a negative I, but when she changes her action, other players might have also changed their actions, okay? So from the perspective of player I, this cost function is not stationary, and we also call it a banded feedback because she can query her cost function only at a single point. The next time the cost of other agents, the action of other agents would change. Intuitively think of if, for example, she observes that her cost went down after playing this, it might not be because of her action, but it might be because of action of others. So what we have to think is how do we estimate the gradients using zero order information, 1-point function evaluation. Okay. And this idea has actually also been in the banded single player setting. The idea is that we need to introduce randomization. Okay. So player I chooses, so she wants to estimate ji gradient with respect to her own decision variable at a point mu I. She samples from a distribution. In this case, we consider Gaussian with a mean 0 and sigma, and she plays a perturbed action, mu I plus omega. And then she receives the feedback. And it turns out that a scaled version of this cost function, where the scaling is by omega divided by sigma, on average is an approximation of her gradient. Okay. And Gaussian is not the only distribution you can use. You can also use uniform, but for our analysis, we focused on this. And this idea is the main idea that we're going to explore, because with 1-point evaluation, we can approximately estimate the gradient. And furthermore, we can characterize the bias and variance of this gradient estimate as a function of sigma. And this becomes useful in our algorithmic analysis. So the algorithm for learning Nash equilibria, I just write it in the unconstrained setting because it's simplest to explain. But if you had the constrained setting, you would do a projection. But it very much looks like a gradient descent, except that we don't have the gradient. So each player samples a random vector from this should be mean 0 sigma t I because her action is in RD. And then she plays that action, she receives the cost, and then she updates the state of the algorithm. So mu I, player I's decision variable at t plus 1 is a function of previous one times eta t, which is the step size or learning rate, times this scaled version of the cost function.
This is the single point approximation.
Exactly. So it's similar to stochastic gradient descent, single point approximation of the gradient descent. And we know that actually it's known that it converges in convex optimization setting. But the question is, does it also converge to a Nash equilibrium in convex game? And the answer is in general, no. We need further conditions. And one condition that's sufficient is that this game pseudo gradient be is strictly monotone. But let me define monotonicity. So monotonicity says that the pseudogradient evaluated at A minus the pseudogradient evaluated at A prime inner product with A minus A prime should be greater than or equal to 0 for every A and A prime. The strict monotonicity would require that this inequality be strict, and then a strong monotonicity requires that this inequality be on the right hand side be the norm of A minus A prime. Okay, so it's very similar to a convexity, strong convexity, strict convexity. And in general, we know that if the Jacobian of this pseudogradient map is positive semi-definite, M is monotone. If it's positive definite, it's strictly monotone. So under this condition, given M is strictly monotone and Lipschitz, we can show that there exist suitable choices for the step size and the variance such that mu T converges to the Nash equilibrium almost surely. So the iterates, this is the stacked iterate of all players' actions. Furthermore, we can quantify the convergence rate under a strong monotonicity and differentiability of this M. And the convergence rate in expectation to the Nash equilibrium is O1 over root T, which matches the stochastic optimization with banded feedback rates. Okay, and this problem I've been working on it for the past 6 years, and we have been sort of refining the results and extending them. But the very first one was the convergence to Nash, and at the same time, actually, that we have our results. A similar paper was also published using the more idea of mirror descent to have but 0-point evaluation of the functions rather than gradient descent. So it's a generalization. I will the proof idea, I briefly talk about it. So it's just to look at the expected value of mu T plus 1 minus A star in 2 norm and show that it has a sufficient decrease. So if we write that, we can equivalently write the algorithm iterates at mu T plus 1 is mu T minus eta T times the true pseudo gradient plus a bias and noise. Remember, we don't have true pseudo gradient because we don't know J's and we only use a single point evaluation. And then we can show that these extra terms are of certain order dependence on the step size and the variances. So by controlling the step size and variances, we can show convergence of this norm of mu T minus A star. And from after that, and using a strict monotonicity of M, and the fact that this step size is not summable, we can show that the convergence of mu T minus A star is actually to 0. Okay, so one of the generalizations we addressed was also learning Nash equilibria in games with coupling constraints. So here, so far, I assume that player I's action AI is decoupled from other players' feasible action set, but we can also consider generalization when there is a coupling constraint. And here we look at generalized Nash equilibrium problems. We also address non-strictly monotone games. I just say a few words about that because I think there are several people also looked at that and have contributed to this. So I'm happy to discuss that. So here, the simplest example of non-strongly monotone game is a zero-sum game where one player is maximizing A1 over A1, the product of A1, A2, and the other one is minimizing. And it is a non-strictly the pseudo gradient is non-strictly monotone. You can just look at the Jacobian of it, and you see that it's not symmetric. And it's known that a large class of convex learning algorithms diverge. There's been a lot of remedies, such as extra gradient proximal methods. Volker and Professor Chepper also had new algorithms with improved convergence rate. Most of these algorithms, to my best knowledge, they assume availability of stochastic either gradient or stochastic gradient or use an extra gradient approach. And we wanted to have a single point, again, function evaluation and a zero order approach. So what we proposed was just a regularization. So this algorithm looks exactly like before, but we have a Tikhonov type regularization where epsilon t is the regularization parameter. And then the only challenge in analyzing this was what should be the rate at which epsilon t goes to zero, so that we can have how we can coordinate that with these other two terms, eta t and sigma t, that are so that we converge to a Nash equilibrium. And in this case, the Nash equilibrium is not unique, so we go to a minimum norm Nash equilibrium of the game. This is just a simple illustration of without regularization algorithm iterates for the simple zero-sum game and with regularization. Okay, so I think with this, I will move on to learning in non-convex games. Are there any questions so far?
What was the scheduling of some T?
It depends on sigma t and eta t in a non-trivial way. I can maybe show you on the. No. It depends on both of them. Yeah. And this is a bit challenging to tune. And also, we could not derive any convergence rate. So I would be happy to discuss, not in the zero order case, but I know that there are convergence rates for the first order case under certain assumptions. But yeah.
What the most limitation of this method?
Okay, that's a good question. I think the most limitation when I think of real world problems, a lot of times you're not completely black box, you know, perhaps something, and how to incorporate that information into the learning so that you can speed up convergence, have a more general convergence results. So that I think is interesting. Other question. And I mean, the convergence is also slow because it's zero order and the variance of the estimator is very high. But more practically speaking, I think this is a big assumption that it gives us a understanding of this problem class, but maybe for reality, we should try to incorporate some knowledge about the problem. Okay, non-convex games. So obviously there are more general problem class, such as auctions, autonomous cars, adversarial training. And we know that Nash equilibria may not exist and in general, and they're also known to be hard to compute. So what should the players learn and how? So we can think of the game as adversarial bandit problem. As I mentioned, in a learning problem, the feedback information is bandit, right? So let's look at the connection with an adversarial bandit. So the decision maker submits queries the function at a given point AT, which is a black box, and then she receives a cost JT of AT. And in a game, of course, the JT, there's no time varying cost function, but because the cost of player depends on action of others, and those are changing possibly based on the action of others, this becomes like an adversarial bandit problem. Okay, so adversarial means that this cost function at each time could be chosen in an adversarial way dependent on action of others. This is a more general so games are a subset of adversarial bandit problems. And in these problems, a benchmark for an algorithm is no regret. So the regret is the total cost incurred up to time t minus the best cost in hindsight. Had the players knew the cost functions in advance. This is a good benchmark because there are algorithms that achieve no regret. And furthermore, there is a connection between games and no regret algorithms. In particular, we know that if players are playing a no regret algorithm, the game action, the empirical distribution converges to a coarse correlated equilibrium, which is a loose notion of equilibrium. But let's now talk about algorithms. So if we let n to be number of actions for a player and t number of iterations under banded feedback, which means that player only receives the cost function evaluated at her action, we know that regret grows as square root of t n log n, the best known, the best rate and the lower bound. And on the other hand, under full feedback, so if the player observes the entire function for JT for every action, regret grows as root t log n. So you see that the dependence on n is dropped, and that's because in one iteration, player is getting n times more information. And what we try to address is, can we consider still some feedback model that's not quite banded, not quite full feedback, and improve this regret rate. So bridge the gap between these two rates. So, oops. So let me give you the idea of the algorithm we proposed. To do that, first I will tell you about the no-regret algorithms that achieve optimal rates. So one class of algorithms is exponential weight algorithms. So you initialize WT, is a set of weights on the actions. You initialize them, for example, with uniform distribution. At each time iteration, you update these weights. Okay, you update the weight of action K, and the way you update it is is in a multiplicative way. So there's a multiplication with the exponential of the cost incurred. So the banded feedback, you will use JT of K, so the cost received at time K, and in a full feedback, you will use you will update the weight of every action using the full cost function. Okay. So then the idea of our approach was, how about we estimate, given that this is a game and the cost functions are actually not time varying, what if we can estimate these cost functions, let's say with J hat IT, and we mimic the full feedback. Okay. So this is one of the ideas. And the second idea is, once we actually estimate, because this is an estimation, and we might have error in our estimation, we introduce some uncertainty around this estimate, and we try to use an optimistic version of this cost function. Okay, so if we use exploration to minimize the uncertainty in the cost estimate. So for example, this picture is from the analogy of bandits with a playing in a casino, and you pull an arm and you get the cost or reward for that arm. And it's saying that by observing, for example, the cost of this arm in many real world problems, you can also infer something about the cost of nearby arms, because nearby actions give you similar cost. It obviously probably doesn't hold in a casino, but in a real world problems it might hold. So by receiving 1 point feedback, we want to estimate the functions so that we can mimic full feedback. And for that, so we introduce an estimation. I think, so an estimation using Gaussian processes, which for the sake of time, I don't go into the detail, but basically we use an optimistic estimate of these cost functions, which has a mean function minus some standard deviation. It's with high probability a lower bound on the true cost function. And using this estimate, assuming that the player's costs come from a GP prior, we can show that the regret grows at root T log N. So the dependence on N is dropped, plus gamma T root T, where gamma T is how much we can remove uncertainty about these cost functions by using this banded query. Yes, exactly, yes. Okay, so I presented at a very high level because of time limitation. It was more about the idea, and this is a work with my PhD student, Pier Giuseppe, and then collaborators, and we have extended it in several ways, generalizing to contextual games, robust optimization, mechanism design, and multi-agent RL, and we also applied it to several real-world problems. I will briefly talk about the multi-agent RL setup. So here we have player I's state, SH plus 1. It's a dynamical system. SH plus 1 is a function of the state at time H, an action of every player plus some uncertainty, and this F is unknown. And AIH is player I's action at time step H. SH is the state of the environment. A policy is a map for player I is a map from S to AI. And the players want to optimize, each player I wants to optimize her objective, which is a sum of rewards that depend on the state of the game and her policy and policy of other agents. And the idea of algorithm, again, was based on this GP regression. We estimate these Fs using a GP based on playing a policy and observing the state. And based on that, we have an we estimate the value functions VI with an uncertainty bound, and using that, we use that to update the player's policy, and then we can characterize the regret rate of this and show that it is sample efficient with respect to the number of actions and number of states, which is one of the bottlenecks in multi-agent RL problem, the exponential dependence on the number of action of players. And I just show one simulation. It was a case study from autonomous driving based on a smart autonomous car simulation environment. Here, one instance was the cars, there's two red cars that are being controlled, and they wanted the white car, which is in a box, is a human driven car, and they want to basically, the red one above wants to merge to the human driven car's lane, and they can basically coordinate and do this as quickly as possible. If they don't coordinate, they might kind of be slow and stay behind the human driven car. And the unknown transition function is the unknown human driven car's behavior. A reward is progress towards the goal and satisfaction of constraints. And SH is the position and velocity of the cars, and AIH, the action of each player is the heading and the speed, and the pi I, there was it was parameterized by a neural network based on what the smart environment provided as a baseline. And I just want to highlight that here we see that if we look at the single agent optima and look at the average agent reward and versus multi-agent equilibrium, it seems that coordination has led to better rewards, slightly higher rewards. This is a comparison with other methods to do multi-agent RL, but maybe I'll just focus on this one, which is a comparison with a model-free method, for example, independent deep Q network. And in the green, you see that the model-based approach converges much faster than the model-free approach, as we would predict. Okay, so in summary, I discussed the problem of learning in games and talked about learning in convex monotone games using the idea of one-point gradient estimators and regularization for non-strongly monotone games, and then learning and no regret in non-convex games based on the idea of estimating the cost functions with some uncertainty bound and exploring optimistically to minimize the regret. So I would like to acknowledge my collaborators for this work. The convex game is with my collaborator Tatiana Tatarenko, who's at TU Darmstadt. The non-convex game is with Pier Giuseppe Sessa, my student who graduated in September, Ilya Bogunovich, who's a graduate of here, of Vulcan's group, who's a professor now at Imperial, and then Andreas Krause. I thank you for your attention and happy to answer questions.